So no, we know about the data files, right? What data files do we have? So we have O, not 0O. That's data file 0. And what do we use the O designator for? Yeah. And then we have data file 1, which is identifier is I, and what's that for? Input. And we have data file 2. This is what? Status. We'll look at that a little bit. And then we have, which is data file 2. Then data file 3 is our B files. Yeah. And we start off, by the way, so these are understood, so we don't have to put the data file number. But anything above that, if we want to address anything above that, we have to put the data file number, right? You understand? So I'd start off and I'd have to put data file 3, and then it comes up and we put a colon, right? And then what comes after that? Not yet. A word number, right? Okay. And then we might put a slash, and then we might put a bit number, right? That makes sense? Okay. Then this is where people got off confused. So timers, anytime I want to use a timer, we have to assign it an address of T, right? You understand? And then we have to just identify the data file number, right? You understand that? And then we put a colon, and then we might put a number right here. And then we're going to stop right there because this is timers use three words. So we don't have to identify the word. We just have to address the timer, right? You understand that? Everybody okay there? And the X can be replaced with any number from what? Yeah, 0 to 255. Now, on some of your PLCs, it gives you the ability to assign these also. I think I showed y'all that. So we could have T4. We could also have a T9 file. So T identifies it as a timer, but then it also, the number identifies it as which file. These are all your default files right here. And what in computers, what does default mean? Yeah, default. Default means this is what you use. This is what the computer uses unless you tell it something different, right? You understand? So these are all the defaults. So these are defaults. And like I said, so what RS Logic 500 does, it goes ahead and assigns this memory to these files right here. New PLCs don't assign any memory to anything. It's up to you to decide. You to assign that, right? You understand? Here, so what we have here is that these are assigned. These are built in, and then we have the ability to add additional ones down here. Yeah, I showed you how to do that, right? Yes, no. So how do we do that? So let me bring up RS Logic 500. And then, of course, well, what do we need to do now? I've already connected to this. I'm going to go to comms and make sure I have a PLC out there that I can connect to. And there it is right there, so we're okay. Then as soon as this goes away. Mm-hmm. Mm-hmm. So what we do next, we'll go to what? Go to new and select to find our PLC in here, right? And this is the 1100B. Then what would we do if we had any extra modules? we would have to come up to IO configuration right here. And this is where we would actually select the modules that we have. And we don't have any for this PLC, but we have them for this one right here. Okay. So if I wanted to add more data files, so here's the default data files. So we have a binary, or we call B3s. This is where we're going to use our internal. This is where we use these for our internal relay coils, right? You understand that? And we also can use it for other instructions. We'll see. We'll use these. I forgot. We got shift instructions: shift left, shift right, which are really cool. That we'll go into. Timers are T4. Counters are C5, right? Control register, we'll be using that register again. There's no register in here that we're not going to be using this semester. So we'll be able to use not registers, these data files. So what I'm going to deal with is some of our counters and our timers automatically deal with integers, but we're going to be dealing with math this time. So we're going to be doing add, subtracting, multiplying, and dividing, right? Understand? And you have to specify where you're going to get your numbers from and where you're going to put your numbers at, especially your answers. So your answers, if you put them in the end data file, it's going to be truncated, and all you're going to get is integers, right? And what is an integer? Well, there's a lot of numbers. So an integer is a number, but a number don't have to be an integer, right? What I say is a Ford is a car, but a car don't have to be a Ford. So an integer, you're right, an integer is a number, but that F register is also numbers down here. So what is an integer? It's a whole number, but it's a signed whole number. So it can be negative or it can be positive, but it has no fractional component. There's no fraction in an integer. So what's floating point? These are the numbers that are signed, but they can have fractions. And they also use engineered notation. Not engineered notation, they use scientific notation. So it's like your calculator. When you exceed the range of your calculator, what does your calculator automatically do? It jumps into scientific notation, right? You understand that? And we see that all the time with our calculator. So once we exceed the range of what we can do without using scientific notation, then this guy here automatically uses scientific notation. Not engineered notation, scientific notation. Y'all know the difference between engineered notation and scientific notation. What's the difference? By threes, right? Engineers by threes, scientifics are by ones. So you might have 10 to the minus 1, 10 to the minus 2 to the 3. So big. Now, if we wanted to create more data files, then we would come up here, right here on this guy right here. I'd right-click on that, and I'd type in what? New. Then we got to say what type it is. So if I needed another B file, then I would choose binary. Also, I've got what? I've got timers, counters, integers, floating points, and we'll look at strings and stuff like that later on. Long. Long, by the way, these are double words. These are double integers. So that if I use that, if I add one of these, so this is not even there, but if I add a long word, then all of a sudden we're going from 16 bits to 32 bits, right? You understand? Which would be big numbers. But we only get 2 to the 32nd. I'm sorry, 2 to the 31st. Because we lose one of our bits for the sign, right? So let's say I wanted to add another B3 file. I'll come up here, I'll add that. Automatically, it's going to choose what file number? No, 9, because B3 is already assigned. What I'm doing is adding another B file, right? You understand, or binary file. Then you'll give it a name, so we'll call it B9. And then I'll come up here and say, okay. And now all of a sudden we got a B9 file down here that I can use as internal contacts and internal relays and stuff like that. So, everybody okay? So if I run out of counters, what can I do? I can make a new counter file, right? Or make a new data file. You know. To get rid of it, I'm just going to right-click and choose what? Delete. Okay. So that these are open to the user. So these down here, these are assigned, right? You understand that? And then these are assigned by the user. 9 through 255. So you can set those up for different things. Some versions of RS Logic 500 PLCs allow the user to assign 9 through 25 to indicated identifiers. So still we have to use these identifiers right here, except for messages, but we'll talk about those later on. So everybody okay here? These are contacts. These are contacts for relay logic. How do we identify these? So we have two categories of timers. What's the two categories of timer? Yeah. Yeah. And then we have off delay. So if I was going to come over here on my PLC and I was going to hook up, I had an external timer, actual timer, then what I would have to do, of course we have a common, right? And then we come over here depending on whether we're syncing or sourcing. And then I would come over here. Well, over here, I would have to use the symbol, the symbol for the actual contact. Now inside our PLC program, all our contacts have this symbol right here, right? You'll understand that. So we don't identify it off delay or on delay. Where we would have to do that is if I was using a contact off a external timer to actually input into our PLC, then we would have to use these symbols right here. So on the wiring diagram for your PLC, you use the electrical symbols, right? You understand? And then inside your program, you use the symbols that are available to us. So how do you identify on delay? How do you identify off delay? The arrows. Okay, if they point up, if they point toward the contact, it's a what? On. If it points away, it's a what? Off. So this would be a normally open on delay. This would be a normally closed on delay, normally open off delay, normally closed off delay. So that was on y'all's last final, right? Two types of timers, on delay, off delay. We already know that. Off delays. When does off delay start timing? When the rung becomes false. So what happens as soon as and this is an output instruction, so our timers are output instructions. So where do they go at? They'll go on the right, right? So here's L2, your timers will come over here. And then we got two simulated coils. What's the two simulated coils, y'all remember? Timer timing and timer done, right? Yeah. No, I'm sorry, enable. Timer timing is one that we don't get. So y'all take. Yeah. Then we come over, right? Okay. So an off delay, as soon as I come up here and energize this timer done is going to come up what? True. And all your contacts are going to change instantly, right? You understand? And then when the run becomes false, then this guy's going to time out. So normally open contacts close and normally closed contact open. Normally open contacts close. Normally closed contacts open. When the timer is finished timing, right? Contacts revert to their normal state. This is not an off delay, is it? This statement right here. Yeah. So this slide's wrong. Because on delay start timing instantly, right? And that's what this is saying right here. Y'all okay? Y'all understand that? I don't know how that thing. Make sure I save this. Starts timing when the timer coils are de-energized. That is off the way. Hold on. Let me read this. Starts timing when the timer coils are de-energized. This is right. I didn't see this. Normally open contacts close and normally closed contacts open when the timer finishes what? Timing. Contacts revert to their normal state when the timer accumulator register reaches 0. So this is right. Is that right? Yes, no? Okay, thank you. RS Logic. So we can address these guys, by the way, guys. But what they've done to us is they've given these registers inside the data file, they're giving these registers names. So this would actually be the address of it. So if I wanted to address the preset register, you could use this guy right here. So how would this go? Well, you could use T4, colon, and what would be X? The number of the timer, and then we could put a dot and we could put a 1. So the preset register is actually word 1 inside the timer. Now you can remember that, or the way RS Logic 500 does, it allows you to use a name instead of an address. But whichever way you prefer. You understand that? And we can have how many, and the preset day can be a maximum of what? And why is that? Well, how did they come up with 32,767? Yeah, so what we're doing is we're using a word, but these are signed numbers. So normally with a word, so how do you calculate the number of combinations? Take the base and raise it to the number of bits, right? I'm sorry, yeah. So if it's a word, it's 16 bits, so that would give us 65,536. But what happens is we do what? We lose 1, so that would be 2 to the 15th. And why is that? Because we lose 1 bit for the sign, right? Okay, which would give us 32,768, right? If you divide that by 2. Everybody okay? Okay. But what happens is that means I can have minus 32,768 negative numbers, and I can have only a positive 32,767. And why was that, James? Yeah, 0 takes up a positive slot. So that's kind of weird, where did you come up with that number right there? So you can't have a timer anything above 32,767 because these are positive integer numbers. And so what if I needed to time longer than that? Yeah, cascade. I hear what Chris said with cascade timers. In fact, we probably wouldn't use 32,000. We'd probably go up to like 10,000. The accumulator register, we could use this address right here. It's actually word 2 inside the counter. Inside the timer file. But instead of using this address, we can come up here and do what? Use ACCA, and this would be the actual ACC. This would address the accumulator, and then so what does the accumulator do? What's the function? What's the preset? So what do we put in the preset? These are timers, but you're close to it. Sorta. Because we combine that with a what? A time base. So to come up with the time, what do we actually have to do? Yeah, we take the preset times the time base. And of course, this would equal the time, right? So if we had a time base of 1, then that would be the preset, and the preset would be the time. If I have 0.1, then that means if you put 100 in there, if you got 0.1, then that's going to be 10 seconds, right? The accumulator, this is going to show us, what does the accumulator show us? Oh, the time the timer has been timing to, right? Okay. And then what does the status word do? Yeah, the flag bits. By the way, the books call these registers. Technically, they're not registers; they're words. So if you look up if you wanted to find this inside the document, you wouldn't say registered; you'd say status words. Time base. Which ones can you can access directly? You can address that one. You can address this one. You can't address this guy right here. I'm sorry. You can't address the time base. So those are definitely constants. So once you put a time base out there, the only way you can change it is to do what? What's the difference in programming? What's the difference between a constant and a variable? That's not exactly true. That's true in math, but it's not true in programmers. So what's the difference between a constant and a variable? No, in programming, any program I've ever written, a constant, you have to change the program. You have to technically take that sucker offline. You have to bring it up, and you can change constant. Right? You understand? A variable you can change while the program's running. So it actually can change. Yeah. But you're right, in math, constants you don't change. So our constant would be like pi, right? Square root of 2 would always be what? So you can't change the square root of 2. Square root of 2 is square root of 2, right? But in programming, a constant means I actually literally have to change the actual program itself. So time bases, we can't address the time base. So once I select the time base, then that is the time base, right? You understand? And how would I change the time base? I'd have to go offline. I'd have to change to a different time base, and then I'd have to download it again, right? You understand? The preset and the accumulator, if we put a number in there, then these are going to be constants. But if I assign it to another data file, then we can put anything in those registers we want to. And we'll show you all that. What's the status flags that we have? We already looked at 2 of them. What's 2 of the stat? We have 3 status flags for timers. What's the 3 status flags? Timer timing, timer done, and timer enable, right? So we have that. Timer enable we usually never use. But we do use the timer timing, and we do use the timer done a lot. So this is actually, every time you create a timer, it actually sets up, this is right out, this is not in your book, by the way. This actually shows you the registers that the words that this thing sets up. So every timer you specify automatically takes 4 bytes of memory. 3 bytes of memory. So if you went up to all 255, it would be 3 times 255 for every timer that you set up. So word 2 would be the accumulator, word would be the preset, and then this would be flag register right here. So they waste all these bits right here. So I could address the enable bit by saying, timer 4.0 for word 0/15, and that way I could address this guy directly, but we don't have to do that because why? Because they've actually gave this a name, right? So if I wanted to address this enable bit, if I wanted to address the done bit, what would I say? I'd say T, and right now we're using what? 4. Then I'd put a what? Colon, and then I specify which timer, right? Maybe 0, and then I could put a what? A slash, and then a what? Done. or I could say T4, right? 0.0 slash 15. And that would give you that same thing. So this would be the way I address it directly, but that's no fun because, well, that would be fun, but this is a lot easier, right? So what they've done is they've given the bits a name. So now since it's got a name, that's kind of like a symbol, right? So once we give an instruction a symbol, then instead of knowing the address, we can do the what? We can use the symbol. So these symbols are built in. So these symbols are built in for us, and it makes addressing these bits a lot easier for RSLogic 500. So this is the accuracy on the time base for the MicroLogic 1000. So it actually gives you the timing range. So the MicroLogic 1100, has three multipliers. It has 0.001, it has 0.01, and 1.00. And this shows you the maximum that you could actually go. So if I used a 0.00, then the maximum I could have would be 32.767 seconds, right? You understand that? Or is that? So we use T4. That's the address we start off with, right? But in actuality, on this PLC, I can have multiple timers, right? Data files, so I can assign them. By default is what? By default is T4, and then I'd put a what? A colon. Then I would put the timer number, right? And of course, what actually limits the amount of timers? So basically, what limits the amount of timers you can put into a program? It's how much memory you have in your PLC, right? Because every timer takes up a whole word of memory, 3 words of memory. Time base, everybody okay with that? Okay. So it depends. I don't know the multipliers on the 1000. Anybody? What's the multipliers on the 1000? Y'all remember? Yeah. I know all of them's got 1. Now this is something they changed on RSLogic 5000. Is you don't have a multiplier. All your time is in milliseconds. So that's a big difference between RSLogic 500 and RSLogic 5000 PLCs. You don't specify a time base. All the time's in what? Milliseconds. So you got to be really good on your multiplication. So on RSLogic 5000, if I wanted a 5 seconds, I would use 5000. But it did away with the multiplier. Here's our 3 flags that we can access inside the timer. Here's the actual address, which we don't really have to use, right? Because why? Because they've given these bits names. And then, of course, we know that we, on some Allen-Bradley PLCs, we can address, we can set up additional timer data files. Let's take a break. On, right? And what's the time? It's set up the time to 5 seconds. Everybody agree with that? Because we're using a multiplier of what? Are we okay? Siemens, when you set the time, you actually say S, you put the time and you end it with an S, it's going to time in seconds. If you put MS, it's going to time in milliseconds. It's really, really neat. RSLogic 5000, all your times are in milliseconds, right? And then we have one of the most powerful instructions this style lets us to do. They call it a move, but it's actually a copy. And what does the move instruction let us do? y'all can read, right? So it's going to let our data file into another word or data file. So what two words what words could we actually change inside a timer if we needed to? Yeah, we could change the accumulator. We could change the what? PRE, or we could change the status. Yeah, we could change. We could write anything we want to into those. Right. I can't do this on our PLCs because we don't have enough inputs. So what I've done, I've used Logic Pro. And Logic Pro is simulating a 504 modular PLC. So we have 3 input ports, 3 input modules, and 3 output modules. So we have module 1, we have module 3, and we have module 5 for inputs. And then we have module 2, 4, and 6 for outputs. So we're going to play around over here. So what I'm going to do is I'm going to use this module for control, and this is going to be the work. I'm going to use this module to actually load what I want to. So if you look at my address, I got to move input :3, and I stop right there. So what does that mean? So right here, this is the address I've got. I've got input 3, and then I stop right there. I don't put a bit number. Input :3, sorry. So what does that mean? Yeah, well, the colon separates the type of instruction. It separates the data file from what we're doing, right? You understand? So I'm going to put input :3, and I'm not going to put a slash. So what does that mean? That means I'm going to grab the whole word. I'm not going to grab a bit. I'm going to grab the whole word. So what I'm doing, I'm taking whatever I'm putting on this input over here. That whole word. I'm going to grab this whole input right here. Right here. And then I'm going to move it. Where am I going to put it at? Into the accumulator. So I can come over here and let me, am I on run? So this right here, that would be 15, right? Y'all can see what I'm doing? 0, 0, 1, and 2. That would be 15. Everybody understand that? Because it's the binary. So in binary, let me bring up my PowerPoint. Looks like I closed it up. So binary, we start off with these bits, right? And we can have up to what on this one? We could have up to 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And it goes what? It goes 1, 2, 4, 8. What comes next? 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 16,000. I lost it. 16,000. And then this would be 32,000 right here. 32,000. Anyway, what I've done is I've got these 3 switches closed, and then I got 0. So that'd be 1 plus 2 plus 4 plus 8. That would equal to a 15. We okay? So that means when I come over and hit this switch, I'm in run, and I'm going to come over here and it says it's going to move whatever I have on input 3, which is a 15. I'm going to move that into the accumulator. I'm not going to do that one. I'm going to do the preset because the accumulator is going to go back to 0 because it's disabled all the time. This would work pretty good on a retentive timer. But what I'm going to do is I'm going to change the preset. So I'm going to come over here and just touch the preset button. So I must download. Undoubtedly, see it says it's in run mode. And notice what happened. It loaded in 15, right? All right. Oh, wrong one. This one. And then I'm going to do this guy right here, which is 2. And what did my preset go to? 15. I'm going to come over and just randomly switch numbers. And then I'm going to hit this again. And then if you were to take this big old binary number over here and convert it into decimal, then it would be 3,503. So what I'm doing is I'm taking any number out. So this would be a variable, right? You understand? So I'm changing this number. I'm in the run mode. Okay. And then, of course, now, if I come over here and hit the 0, then my timer starts timing. But I could actually change this on the fly, right? Okay. So I could do I could come up here and hit the first button. Of course, it's going to time out. But what did it do? So here I moved that number into the what? Into the accumulator. So what we're saying is that with that move instruction, I can use these presets and these accumulators, and I can literally put any number I want to in there, right? You understand what we're saying? Which is pretty neat. This is pretty neat though, because I can actually change these over here. And what's the maximum I could put into that? Let's see if RS Logic 500, if the simulation lets me do that. This guy, he does a real good job, but sometimes he lets us get by with things. So literally, I should not be able to load this number in there. And why is that? Because I got bit 15 set to a what? To a 1, which is automatically, that makes it what? A negative number, right? Understand? We can't put negative numbers in timers. So we'll see if this guy lets us get by with it. So I'm gonna come up here and hit switch 2 again. So yeah, it loaded a weird number in there. Oh, because this switch right here is closed. So RS Logic, this simulation is pretty good. But this, I shouldn't be able to load this number in there. Oh, wrong thing, Rich. This guy. Yeah, so instead of putting, it took it as a positive number, and what did it put in there? Oh, this is still set. This is still set right here. Let's see. Oh, wrong thing. Yeah, see what it did. So the simulation is okay. In normal PLCs, we've got a problem because I can't have a number this big, right? Yeah. So this guy didn't compensate for that. So I just wanted to see what would happen. So the biggest number we could possibly put into it should be this number right here. So I'll close all the switches except for 15. And what should this add up to be? 32,000, yeah, 767, yeah. Yeah, 32,767. So this guy, but this is a simulation, right? So this is not the real thing. Why I use this is because we had these whole 16 bits. If I tried to use my PLC, it's only got 10 inputs, and I'd have to use two. I'd have to use three of the inputs just to control the timer, right? And we can load the accumulator, but it's not going to do anything right now. But watch what happens when we come up here and start running this thing. So loading the accumulator, we don't do much, but it should work. So let's start it timing. Now see all this, now it came up and gave me done. So we can access, and what I'm trying to say is using this move instruction, we can do the example that the book uses, but you can literally put anything in what. You can put anything in this accumulator, and you can put anything in the preset. Normally we could change the preset, so I could change the preset on the fly, right? You understand that, which makes this a true variable. That makes sense? So this move instruction is really, really powerful. So if I can address any data file, I can put anything in any data file anywhere. I could update my outputs if I wanted to. So let's do another one. So let's go program, I'm sorry. And we won't use any of these, but insert a rung, so I'm down in program. So input, I want to address the whole input, so I'm going to put 3, right? I'm not going to put a slash. In my destination, I'm going to put it into output. To oops. It lets you get by with stuff you shouldn't get by with. So I'm going to assign this to input 1 slash, which one am I not using? I'm using 3. Excuse me? Yeah, I'm going to use this guy right here. Okay. So I'm inputting module 1, switch 3, and then what I'm going to do is I'm going to take this word and I'm going to send it directly to the output port without any control on it at all. Let's see if this guy lets me get by with that. So here comes switch 3. And what happened to the output? So what I could do now is, instead of going through all this logic, if I wanted to set my outputs up, and we do this in PLC3 because we have a reset button, or we can reset. Well, when we hit reset, we want all the outputs to go to a certain state. So instead of me doing what? Instead of me trying to set them up, I just use the move instruction. So I'm going to come over here on these switches, and we'll just turn on every other one. Oops, missed one. Nope, that's okay. Well, don't make any difference. And then I'm going to come over here and just hit this button right here, and my outputs just took that, my outputs went to that state without going in through any decision making, right? You understand? So we can set up outputs any way we want them to by using a move instruction. Right? You understand? I can put anything out there on those outputs. What they do over there on the line is, for some reason, they put 128 out there, which would automatically set bit 8 anytime you do a reset on that line over there. So what we can do is, if we reset, or if we set the line, we can put our outputs into a certain state that we want them to be in to start off with, right? instead of me trying to do this, I can just move whatever value I wanted to there. Here I'm using these switches, but I could come over here and I could, so what this thing does, what that program does is it comes over here and it don't use the switches. Let's see, go to program. It just sets up a value. It sets up 128. Okay. So now when I download it, okay, then I go online, and then every time we reset it, it would kind of close the switch right there, and it automatically turns off all the outputs except what? That one that I want. So this move instruction is a really, really powerful instruction. We can take any data file and put it anywhere, or I can take any constant and put it anywhere, right? Understand that? So it's one of the most powerful instructions that we have available to us. So over there on the AMPRO line, over there, look at that. You got a reset. When you hit reset, if we was looking at it, the outputs would come up and go to a certain state. Now, how does it do that? Well, it just do it with a walk and a move instruction. So here's the one that they showed us in the textbook. Oh, that's the first time I said. Where they're actually using two move instructions. This is going to put 1,000 into it. That's 1,500. I can either time from 10 seconds or 15 seconds. This is still on the left. Yeah, okay, there. Does that make sense? Right. That move instruction is really powerful. A reset. So on a reset, reset. So this is off delay. So when this guy start timing, when the run becomes what? The run becomes what? Off. You know. So right here, they're starting off by making the run true. When this thing, this is time here. Seconds, right? So here the run starts off with true, and then when the run goes false, that's when the off delay timer starts timing. Are we okay on off delay timer? Okay. Like I said, this is a review. And then what's our other type of timer? Off on delay, retentive on delay. And that's not, so what's a retentive on delay? Y'all remember that? Y'all remember that? So on this timer, if we go back to here, so I'm going to come up here and switch this, right? Let's see. Let's put something in there. 128 is pretty good. So I'm going to come up here and I'm going to load the preset register, right, with 128, which is, they show an 8 hex. And then I'm going to start the timer. Sorry, let's close this. Then we'll load it, right? Preset switch 2. We start the timer. Starts timing. Okay, when it hits the time, good gracious, guys, we're gonna be here for a long time. I thought I was doing 128, so yeah, we'll go ahead and switch it while we're doing this. We can actually switch it while it's running. So let me drop off another bit here. Here we go. Oh, I have this switch way up here close. So let's just do 15. We'll load it. Oops, 15, Rich. Reset it. Okay. So here it timed and it stayed solid, right? Okay. And then what I'm going to do is I'm going to disable the timer. And as soon as I disable the timer, what happens to the accumulator value? It automatically goes back. What? It goes back to 0. And so what we'll do is we'll change this to a retentive timer. So here's RTO, okay, and we'll give it the same number, T4:0. And we'll set the preset through a move instruction. Okay, so let's load it with a bigger number so we can see this. So we're going to load it, okay, with 63. I'm going to come up here and start timing. Starts timing. I disable it. What does it do? It holds the number. So non-retentive timers, when the rung becomes false, they automatically reset the accumulator to 0, whether you let it finish timing or not. A retentive timer holds the time, even when the rung is false, right? So I'm going to come up here and start it, let it time again. This is on delay, so when it gets up to 63, we get the done bit. I come up here and make it false. Now it's 63 on there. I can't use the timer anymore because it's timed out. What do we have to do with a retentive timer to start timing again? Yeah, we got to have a reset instruction, right? So we don't have to have a reset instruction with a non-retentive timer because as soon as the run goes false, it resets by itself. A retentive timer holds the time until we do what? Until we use the what instruction? Reset, yeah. So here's our reset instruction. I got to put another rung in here. So we'll trigger it with another switch. Which switch am I not using? I'm not using 4. Input 1:4. 1 input :1/4. Okay. And then we'll come over here in our timer section, timer counter section. I know I went past it, didn't I? And we'll pull the reset down. And what are we going to reset? We're going to reset timer timer 4:0, right? Everybody okay? Okay. And so what we can do now is we can come up here on switch 4 and we can reset the accumulator. Time it, we stop it in. So if I was on a non-retentive timer, even if it hadn't finished timing, if you make the rung false, the accumulator's going back to 0, even if it hadn't finished timing yet. The retentive timer, it's going to do what? It's going to hold the time until we do what? Until we reset it, right? Everybody okay? Interlocking timers. What do we do? What do we usually use interlocking timers like this for? I call them cross-couple timers, but the book calls them interlocking. What does the circuit breaker do? So which one's gonna which one's gonna start time? Which one's gonna start timing first? Should be this timer right here because it's gonna be the first one that's taken. So as this starts timing, contact right here opens, right? When this thing gets up to 50, when it gets up to 5, it gets the timer done. Timer starts timing. This contact right here will close. This guy right here starts timing. Right? Understand? Gets up to 5, gets the timer done. This contact right here is going to open. This contact right here is going to close. This guy here is going to start timing. So what this guy's going to do, it's going to just sit there and do what? Yeah. And what do we use these things for? Flashlights. I've ever been in, they got lights going on, flashing somewhere. We might use it to ring a bell off and on, off and on. If something, when they get fire alarms, the bell goes off. Just on and off, we use it for that. So these are cross couple timers. We'll call them cascade and blocking. So right now this green light would flash on and off and on and off and on and off and on and off. 5 seconds on and half a second on and half a second off. Everybody okay there? Other timing options. This is not in the textbook. We've got 2 other timing options. We have the X4 register, which is a free running clock, and it's counting a 16-bit counter. So you can see if I was to come over here and just these bits right here, let me get more room. So I'm just going to use 5 bits when this guy here is actually 16 bits. So I started counting in binary. 2, 3, 4, 5, 6, 7, 8. I'm gonna run out of room. 9, 10. But for every count, this guy right here is going to divide by 2. Can y'all see why? Yes or no? So the first count, we start off with 0, and then I give it, the run goes true, right? And then we come over here, the run goes true again. Then it would go to 1. Then the run goes true again. Then what would it go to? It go to 0. Then the run goes through again. It go back to 1. So what we do is for every 2 pulses, we get 1 count. We get 1 1, then a 0, then a 1, then a 0, and 1 and 0. This bit right here would divide by 4. This bit right here would divide by 8. This bit right here would divide the input by what? 16, 32, 64. Okay. So that's why if I want, that's why I'm using a half a second to get 1 second, right? So half a second on off and on, actually the light would actually blink every 1 second, right? Does that make sense? So what we have with this 16-bit clock, I can go all the way up to it divided by 65,006, depending on the clock. So this is the layout for the 1100. So here, if I use bit 0, then I get 100 microseconds. This will give me 1, 2. This will give me 1, 4, 8. Now the guy that authored this is wrong, so this should be times 2. So this should be 0, 0, 1, 6. It should be 0, 0, 3, 2, 64, 128, 256, 512. Then this is right? 1,024. Why does Rich make mistakes up here? So whoever authored the book just didn't notice it. So they were down in here, right? Y'all understand? So they were down here instead of being up there, right? But see, it's binary: 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024, 4,009. So if I wanted something to blink for about a second, instead of me using cross-couple timers, I could use what? I could either use this guy or I could use this guy, depending on what I wanted to blink, right? You understand what I'm saying? Yes or no? So what I could do, and I'll show y'all this program right here. So cross-couple timers are nice, but they take up 2 rungs and they take up a lot of time. When this guy's got this free running clock in there for me. So if I was going to make lights flash and I wasn't concerned with it's on 1 second, off 1 second, uh, then what I could do is I can use, instead of using those cross couple timers, let me get to the right place. This is not the one I need. So let me, this is what I want. So here, I'm using, is that restrictor? I'm using S4 bit watt 12. Ah, yes, but that's this. I have to. I'm trying to connect to my PLC. It says it couldn't find one. I'll take a break until I can figure out how to do this. Huh? Yeah, no. What's going on? Yeah, we'll eventually. I think we requested two. So first of all, we have to put in a request for work study. Yeah, we need two. We've got nobody that signed up for it. So normally, when you first turn on most computers, they'll go to what we call a little power on self-test. So, and what it does, usually let you know it's going through there. So notice originally it come up in flash, and then it comes up. And of course, what we're looking for is to make sure this fault light don't stay on, right? And then of course, eventually it'll come up and show you this. Now the MicroLogic 1100, it comes up by default by monitoring the I/O. So this uses this LCD screen here, and on the top row, this will show us the status of the inputs, and then the bottom row will show us the status of the output. Now the 1000 actually has LEDs that light up for each input. This guy right here, this is what you would have to do. You'd have to look at this right here. The problem is that we're using, instead of using the DH485 over RS232, which is what this guy is right here, this is for what we call peer-to-peer, which means if I hook it up to this, I could not network with it, right? Understand? What we're using over here is we're using what they call Ethernet IP, which is the generic term. Siemens calls it Profinet. So Profinet and Ethernet are exactly the same. Yeah, so what we have to do is what we call a crossover table, because these two things, my computer and the PLC, they're both computers, right? You understand? So we have to have a special called a crossover cable, which if you take PLC 3, we'll make these. But what we're trying to do is what happens for some reason is so on Ethernet, on IP, on Ethernet, we have two things that come with a system. First of all, it's just like when I call you, right? I got to know your phone number, right? If I'm going to send you mail, I got to know your address. Well, that's the same thing true on Ethernet IP. Everything on the network has to have an address. And it's what we call a logical address, which means it's assigned by somebody, right? We got two ways we can get an IP address. We got what we call a dynamic IP, which means there's a computer on this network. It's called a DHCP server, which is a dynamic host configuration protocol. So as soon as I turn on this computer, it asks for a DHCP somewhere. And the DHCP server would assign an IP address on the network that doesn't conflict with any network out there. This is what happens when you get on the internet. You have to have a unique IP address, right? You understand? But also, what they're doing, sometimes you can actually see this on your cell phone if you go into the settings. It's assigned a physical address that never changes, and these are called MAC addresses, which stands for Media Access Control MAC addresses. These are built in. So if I was going to build a unit that was going to be on Ethernet IP, I'd have to contact, I think it's IEEE, and then they would give me, they would assign me a set of MAC addresses that I could use. And that's physical. You can't change the MAC address. You can change the IP address, but you can't change the MAC address. Does that make sense? So the problem is, for some reason, I lost my IP address on this computer, on this PLC. So that means I've got to access the DHCP server, find that IP address. Let's follow it so far. Okay. So, but I'm connected to my computer. So what RS Logic provides us, it provides us with a program called, and you'd have to even do this, guys, on RS Logic 5000 if you was going to connect directly to the PLC. Is as soon as I get this, guys. So programs. So inside the RS Logic folder, RS Logic's folder, So here's RS Logics, RS Rockwell Software. They provide me with a DHCP server. And of course, what I have to select the network card that's in my computer, and this is the DHCP server. Sometimes it might not work. So as soon as I turn this computer on, okay, it's going to ask for. Now, what I have to do is I have to know the MAC address, and it's 000F, and then it's a bunch of other stuff. So there it is right there. So I'm going to double click on that, and now it's going to allow me to assign this thing an IP address. Every number up here has to be the same except for because it's on a subnet. I'm not going to explain that. So I'm going to go 169 and then .254 dot 163 and then 163 Rich. Yeah, if you have your network set up, we have something called remote. We have something we call remote access or remote access. Somebody they can call in. Yeah, if you have access over the internet, then people can actually log into your PLC and actually do changes from Chicago. We've had that happen several times. Not if it's hardline directly from the computer, then your computer has to assign it to IP address. Probably not a PLC in an office, a computer in an office. Yeah, I know it's a computer in the office is not necessarily controlling the PLC, but you have the ability to access the PLC. Yeah. So you might have to PLC, well, they all have a separate IP address. And then, or you might want to change time. Well, instead of you getting up and going out to the PLC and hooking up to the PLC, which you still do, you can actually access it through the network. So like I think Bros, they're not in the PLC. They got to make a change to a PLC. They take their laptop out there and plug it directly into them. So I have that part. I have that, right? That was one company was telling me that they were watching the guy make changes with their program, but he was robots. Yeah, only if they have internet access. Only if they have an IP address. Yeah. Yeah, well, it's cool. That's probably where they use simulation software, so because they can't see the robot, but they can see their simulation. By the way, once you assign an IP address to a computer, that IP address is embedded in the program. So what that means, if you give it a new IP, then the program's not going to be able to communicate with the PLC. I'll show y'all where y'all can change that at. What do you mean? Oh, yeah, you're right. Sorry. Here we go. 00, right. Yeah, thank you. 169. So I don't know who I assigned that at. Well, I didn't give it time. 169, 254, 163, and then 100, which is what I normally use. And what's going to happen is eventually we'll see it pop up here, and it'll get that address. And once it gets that address, then we should be okay. By the way, you can see the IP address. And that's what I should have shown y'all guys. I'm sorry. So what I'm going to do is I'm going to hit escape, and it brings up another menu. Here's This is where I can manually switch it between run and program. And if I switch it here, if I switch it to run from here, then you can't change it remotely. Uh, I'm gonna go to advanced, and down here I'm gonna go to the Ethernet, and this is the MAC address right here, 00F. This is where I'd see that, and then down here you can see it took that address. So right now, before this was blank down here. I know it's hard to see, guys. So we're okay now, so we should be able to communicate with the PLC. So we'll see comms. We'll see if we'll see if it's out there. Okay. So here it is. If it can't find it, it would be X over there. So it's okay. So now we're okay, right? This is the same program, so it should be able to go directly online. Okay. And this is this S4. This is in this free running clock. We can see this, not in this status, I think. Yeah, it is. So here's that free running clock right here. Of course, you can't keep up with it. Can y'all see it? No. I'm using bit 12. This would be bit 0 all the way through 12, which would be right here. And that would give us, I think, about 0.8. We could look at that chart. This is available also, guys, on the so I'm using bit 12. So this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's about 1 second. It should be about 1 second on and 1 second off. In the program, you can actually see it going true and false and true and false and true and false. Did y'all see that? So that's it. And then, of course, when I come up here and start this thing, and I don't have my camera on, but it's got this light flashing right here. Yeah. So this would be more efficient to use those interlock counter, those timers, right? And by the way, we have an extremely accurate one too that we can use for timing. So if I was going to flash a light or ring a bell, this is what I would use. Because it takes one rung, right? It's a very simple rung, very few instructions, a very short scan time. Are you okay? Make sense? Now the other thing we have available to us, so these are the actual time. This, if you're on the 11, if you're on the 1000, then if you want it to flash for about a half a second, then you would use off time. You would use about a second. You would use bit 7 because the 1000 is running at a lot slower speed. So ain't that cool? Yeah. We also have available to us the time of day. So we have a real-time clock in this thing that we would have to set because it's been unplugged for a long time. We don't have any batteries in this thing, so if I had batteries in it, if I had a battery in it, but we hadn't been able to find it, Alan Bradley wants to charge the arm and a leg, then it would keep that IP address. Right now, if I accidentally kick the switch over here, which is probably what happened, then I lost my IP address, and I wouldn't be able to communicate with it anymore. Yeah, if you lost your batteries in the robot, you'd lose your origin. So we have a real-time clock in this. So this guy actually keeps time for us, and it keeps a lot of time. So this is what's available on the real-time clock. We have access to a year. So we can make something happen in a certain year, on a certain day, at a certain hour, at a certain time. So if I needed something to run every week, and we could use the real-time clock, like every Tuesday. So look at this bit right here. Okay, where's hours? And then I would look. No, I'm sorry, days. Day of week. 0 through 6. So if I use the 0, it would run every Monday, right? You understand? If I use a 1, it will run every what Monday. It's like that. Yeah, well, we have a cleaning routine. You want something to go out and do it every once in a while, or you might have an HVAC panel. You do preventive maintenance and it pops up like this, right? So the bill don't actually do anything, but it sends a signal to something that says it needs to be done. Turn on a light, like your low food light, your uh, light had the switch on the side where it has levels on it. It has a divider, and when it started stuttering on you, have to reach down the side of your leg and turn it over to what we call reserve. My Honda had a light that would come on. It would turn red when I needed to do what? Well, that's what you do. It didn't turn on again. That you needed to fit. So you could say, okay, this light comes on. It says, okay, that light means I need to go up there and get or do stuff like that. So you literally can set the PLC up to do things at a certain time, a certain year. The only problem we would have is that RSA 500 only takes us up to what? 2097. That we would be messed up. But we could do something on a certain year. We could do something on a certain month. We could do something on a certain day of the month. This is not day. So if I do it like on the 25th of every month, I might want to do something, right? You understand? I could do that. I could do something every hour. This is 24-hour time. They call it military time, but it's actually 24-hour time. Because a lot of people use 24-hour time except the military. I could this right here is what? This is minutes. This is what? Seconds. This would be day of the week, and then these we're not. These are just battery low, and I don't know what this disabled is. Oh, that disables the real-time clock. So we need to be able to set this. So where would we set the real-time clock at? I'm going to stop this. Yeah, but it's still timing because I'm using a timing bit. So it still shows it's going what? True, false, true, false, true, false. But instead of me using those interlock timers, this is one run, guys. I mean, I can make a light flash. I could do anything. Cross couple of those interlock timers. This what that's available for us. Oh, I'm sorry. It's right here in the function files. So function file right here, right over here. Where's it at? Real time clock. And this is where I would come in and set this up. So what year are we in? 2019, right? And then what month is this? Wait, it said it failed. Okay. Typed, right. Oh, I'm in run. I can't do this in run. Say, Rich, you can't do this in run. We can't change the real-time clock when it's in run. Real-time clock. Okay, and what month are we in? 10. What day? What hour? What's 8 o'clock? 2000 minutes? It is exactly 8. Yeah, it is. Wow. Seconds? We'll get that. Day of the week? One, right? Okay. So that's what we just did is set that real-time clock. The problem is there's no battery in this PLC, so if I turn it off, what I'm going to do, I'm going to lose all this. So it's good to keep batteries in your PLC. So. So what we're going to do later on is we're going to look at these guys, and this is what you would use. So there's a timer, and then these are what we call our compare instructions. So one of the things we'll look at once, I think it's actually, I can't remember what's after timers and counters. Is the compare next or is it the math next? I can't remember in your textbook. Right after counters. What's the next chapter? Counters. Math. So we'll do math next. And then after math, we do what? Well, the PLC is going to do the math for you. All we got to do is add, subtract, multiply, and divide. That's master control. That's the master reset. Yeah. We're going to use that. Then what comes after that? CRs, subroutines. Then the bit shift, data handling. Move is the data handling instruction. When do we get compares? When does the compare instruction come in? Compare's got to be in there somewhere. Okay. Math and compare, yeah. Yeah. Jumps. We're gonna learn how to jump. So y'all need to bring y'all sneakers that day, right? Glad you can make it. All right. Give Jalen one of those things. So normally when we get into compare instructions, you'll see how we could actually set that. We could use the second on that instead of the real-time clock. I mean, if I wanted something to blink for 1 second, then I would probably use the seconds up here. Cascading timers. Why would we cascade timers? For higher preset, yeah. So we're limited for 2,767, right? You understand? But if I needed more time than that, we'd have to cascade. And so this in the book shows you cascading timers. This is not the book. This is done with RS Logic, our Logic Pro. So the first one would time for how long? 10 seconds. And then when it got through, when it was done, it would go do what? Shift over this one. This would be 10. And then when it's done, it would shift over to this one. So what was the total time? 30 seconds, yeah. And as soon as I switch 1-0, as soon as I make that false, that's gonna reset timer 0, which is gonna reset timer 1, which is gonna reset timer 2. You understand that? Yeah. And how are these contacts right here arranged? What logic is this? Or, right, good. So the light will stay on for 30 seconds. Counters. What 2 types of counters we got? What's that? What did you say, Chris? Up and down, right? Up counters are easy to understand in Allen Bradley. Down counters are weird. So by default, what's the default data file for timers? C5, right? But we could add more. Everybody understand that now? So all these instructions, their address is going to start off C5:0, and then we don't put anything else because we're addressing actually three bytes, right? I mean 3 words. So what are the registers inside our counters? What are the 3 registers or the 3 word files inside that make up a counter? Accumulator. Same as the timer. We don't have a time base on counters. We got a what? Preset and an accumulator, right? And a status register, right? So count up, count down. The accumulator will increment, and it's going to increment toward the preset. When, on an up counter, when the preset and the accumulator match, then we get a timer, then we get a done bit right through out of the status register. Then what happens? Does the counter stop? No, it keeps counting, right? And it will keep counting until you do what? Until you reset it. A down counter, we only load it with a negative number, right? And then it starts counting down. And then when does the done? So on the down counter for the RF Logic 500, the done bit starts off set, right? You understand? And then how far do we have to go to get it to reset or go to 0? Huh? Yeah, one more negative. Preset, so we can address the preset register. We can address it. We could address it with an with a move instruction too, right? So I can put anything I want to in the preset register, and I can put anything I want to in the accumulator by using the move instruction. What are the flags that we have in the status register? In the status word, what's the flags we have here? We have a what? We have quite a few. We have a lot more. Anybody remember? Nobody remember? So we got a CU flag for an up counter. We got a CD flag for a what? Yeah. Then we have a done, right, which tells us what? Yeah. Well, it's matched. It hadn't really finished. It's matched. The counter will keep counting, right? Okay. Then we have a OV and we have a UV. What are these? One of them's overflow, one of them's underflow. Yeah. Overflow for up counters, underflow for down counters. These guys use, yes, a V. Well, the problem is these are signed integer numbers. So I mean, the maximum I could count to would be a plus what? 30. What's that? 32,000, right? 767. So what happens if I told my counter to count one more? It would. But what would happen is it would set the most significant bit, and all of a sudden my number would go negative. So it'll be a positive number, then all of a sudden it's what? It's negative. So I've got this program out there. Let's just to show y'all that. The problem is on a negative counter, once I count down to minus 32,768, if I told it to count one more, what would happen to the number? It would switch signs on us, right? You understand? So we need an indication of when we exceed the range of our counters. And what do we use? Well, we use we would monitor an underflow bit and an upper underflow and a, where's my thing at? Right here. So let me go to open. I think these are in your, I think these are in PLC 1. Oh, I didn't need to change that. I didn't make any changes to it. So I'm starting out putting numbers in this guy, right? So up there already I have what am I using to make them count? I'm using switch 0. 37, okay. So notice what happens to it. What happened to my sign? Yeah, it was positive, right? And changed what? Negative. And what happened? Well, the overflow bit went true, and I'm turning on the light. Let me see what I'm using for reset. I'm using 2 for reset. Okay. Oops. I need to activate my move instruction. Okay, there we go. So when I reset it, my accumulator went to 0. That's a long time. So right now it's what? It's plus, right? So here we go, right? 66, 67, everything's okay, right? Then what happens? One more count. What happened? Change signs because I exceeded the range, and it told me it changed signs because it activated which bit? That flag, that overflow bit, right? Okay, and then I'm turning on a light. Now notice this guy right here is still okay. Let's keep counting. Now, because this got to go one past, right? So what happened to this one? It started off what? Negative, and now it switched over to what? Positive, and what did we get? We had an underflow. So that's the 2 additional bits that we have that we would monitor with counters. And what does these tell us? Well, these tell us we exceed the range of our what? Of our signed numbers. Switch 2 to reset. Okay. But when it reset, let's see, switch 2. Switch 2. Oh, wrong one. Okay. Reset them. And now what I want to do is I want to put that number back in here. So what am I using? I'm using move instructions, right? Okay. To put what I want to in there. So this is switch 1. Then I load what I want to in there. So underflow and overflow, you don't understand what those guys do. What are they doing for us? They're telling us when we exceed the range of our signed numbers. So if I try to count past 32,767 on if I try to go to 32,768, it's going to switch over to the negative number, right? And of course here I got to go what? This guy's weird. I got to go one past. So notice this one, the done bit starts off cleared. Here, the done bit starts off set. So that one will set when we match, when the preset and the accumulator match. And this right here will clear when we go one pass. Can you say, why did they do that? Well, we just don't know, but they did it that way. So here we go. So here's, now this other one's still negative, right? And I got to go one what? I got to go one past it. So are you okay on the status register? So we have count up, which tells us every time when this guy's enabled. We have count up, and we have done. We have the done bits, and we have the two overflow bits inside the status register or the status file. Are we okay? So here's their actual address, by the way. Which, thank goodness, we don't have to know that because they're giving us names instead of addresses. See, done bit, overflow. Are we okay there? And we already know that. We know that. Know that. So when will we cascade? When will we cascade counters? Probably the same reason we cascade timers, right? We can go past the range, then we can cascade. Usually go 10, not usually 30, 32. So this is the difference, right? So on the count up timer, the done bit changes when the accumulator and the preset match. On the down counter, it starts off set, and then you got to do what? You got to go one past, one more negative, reset goes to 0. We don't need that. That don't work out either way. So this would be cascading. So it's almost just like the timers. So what bit do we use to cascade them? So the first one, we have it. When it gets done, what would it do? Then it'll come and do what? We come and enable this one. We're going to do something. Because why is that? This wouldn't work. Why wouldn't it work? Oh, yeah, well, here's what it does. So this guy counts from 0 to 10. Then it gets it done. It's going to cause this guy here to count 1. Then it does what for us? You see this? Yes or no? So what happens when this guy counts up to 10, then the done bit would set. That would come up here, and that would let one count to go through. This guy would go to 1, and then when it gets down to here, because this rung is scanned first, right? Then it would do what? Then it would reset this one. This would go back to 0. Then it would count to 10. Then this would go to what? 2, right? And then it'd count to 10. It would automatically reset, and this right here would go to what? 3. And this is just an example of how we could actually cascade the timers. We could have one count in tens. We could have the other one be hundreds, thousands, right? Understand that instead of going. So that was right. Can y'all see this one? I don't know if I can. Huh? This is real small. I think this is in your book. Find it in your textbook. This is unfortunately they don't put figure numbers in here. So this should be inside this is going to be inside the timer. So we got a timer up there. It's set the time for 1 second. Can y'all find it in there? Should be in the counter section because that I don't know if I don't have a chapter on counter timers, do you? For timers, well, it's 100 and then it shoots our 0.01, so it's 1 second. And then every 1 second, it's going to increment timer. It's going to increment counter 1. And then when counter 1 is done, it's going to increment counter 2. And it should automatically reset itself. Let's reset it. Count to 40. Timer 2 is set. So it is 60 guys. It's even blurry up here. That is triggered off of counter 1. So that's counter 0. This is counter 0. This is counter 1. This is counter 2. Triggered off counter 1. Well, they have the reset stuck in the center. So the first counter would count. It would update every. Is that 1 second per second, right? Right. And then the second one update every 60 seconds. And then the next one would, this is the clock, guys. Can y'all see that? It's a 24-hour clock. So this is giving me, this is, guys, every second, it'll count here. This guy's going to count from 0 to 60. And then when it's done, it's going to trigger this, and then this is going to count from 0 to 60. It's going to count. So every second, this right here would go what? 1, then it go 2, then it go 3, 4, 5, then it got up to 60. Then this guy right here would go to what? 1, right? And it'd go 1, 2, 3, 4, 5, 6, and then when it gets up to 60. Then it's going to count this one. This is set for 24 hours from 0 to 24. So this is the clock. And then they should reset themselves. So when this guy gets done, it resets itself right here, right? When this guy counts to 60, it resets itself right here. And then when timer 2 gets to 24, it resets itself right here. So this would be a clock. A 24-hour clock. Of course, we don't need a 24-hour clock. What's that? With this PLC, we can use a real-time clock. Right? This is a key problem. So this we're combining what? We're in the first lab that we're going to work on, guys. This is the kind of stuff we're going to do. We're not going to do a real-time clock, I don't think, but we're going to combine timers, counters. Yeah. So we'll be ready to go to lab next class. So let's get out of our lab book. I don't have it. Let's find the first lab. Wait a second. Let's do this. Yeah, hand these out. And we'll go over these and then we'll go. So the lab procedures are pretty close to what we did last class. So what do y'all need for every lab? Yeah, the lab form, right? And we're going to start right after, we're going to start in the timer counter, which is what we're doing. Probably 10 dash something, right? Okay, so 9-7. Okay. So it's inside the. This should show y'all which ones we're going to do. So one of these sheets here, if my thing works. So here's our labs. So we're going to use 9-7 activity 1. So we should be able to work on that starting next class, right? Then we're going to use 10-1. This is our math instructions. Plus you got to make sure you read the instructions here, right? This is going to save you some heartache. Ladder diagram must be drawn to perform each individual math instruction in the space provided below each description in the lab book. Create a ladder diagram using RSLogic 500. Name the ladder diagram using the syntax set to another page. The program must include a rung for each math instruction. Use 2 move instructions for 2 word operands. So what we're going to do, we're going to do for math. We're going to take the same 2 operands and we're going to add them, we're going to subtract them, we're going to multiply them, and we're going to. And how are those operands going to get in there? They're going to get in there by move instructions, right? You understand that? So what you get these labs, you make sure this, because this is going to explain a lot more in detail what you need to do with each one of these things. Draw your final PSC line diagram on the back of the last page, or on a what? On a separate piece of paper. So we're going to do activity 1 in lab 10. We're only going to do lab 20, activity 1. I'm sorry, activity. In activity 11-2, we're going to do, in group 11-2, we're going to do 1 and what? 1. 11-2, we're going to do what? 1. Then our compare instruction. Here we're only going to do 1, 1, 1. In fact, the only time we're going to get into 2 when we get into so. So these are the actual labs. The labs are right. And in PLC, I mean, guys, we're going to be in a lab. We're going to be in a lab Wednesday night. We'll come up. We'll start off in here. Get some things we need to talk about. So here we're basically going to be in a lab almost every night. So we should be able to get through with most of. I'm going to say all of them. Some groups are going to get through with all of them. Some are not. I've never. So lab form, you're going to sign your name up the top or in a sign off in a lab form. I mean a sign off. Everybody's going to have a lab form, right? Everybody okay? No short pants or open toe shoes. I've got a grandson and he wears shorts all shorts. So he wears shorts year round. So guys, we're going to hold you to this these lab procedures, right? So I'm not going to be as lenient this time as we were last time, right? Okay. So I need to look these over. Shows you how you're going to be graded, how I'm going to subtract points. That's on here. Shows y'all a sample of the lab form. You're working in groups of 2 once everybody shows up. Then you're going to take turns constructing. Actually, One person's going to be at the computer, the other person is going to tell them how to enter the program, right? Just like last class. So any questions on counters and timers? This is one of those big now forever things, right? While we went over, this is a review that we had last time. This was where we ended up last class, right? Some of y'all has been off. I think Jalen. And when did y'all take OCR? Y'all been out for? Y'all take it during the summer? Okay. So y'all been away from this for at least 8 weeks, right? 10 weeks, really. So if y'all got any questions on these, like I said, that's why we start off with a review. Then next topic we'll go into is math. And math is not extremely hard, guys, because it's just addition and subtraction. The only problem we got to be careful with is when we divide two numbers with a fraction, yeah. So which register are we going to use for our division? To store our answer for our division, where we're going to store our answer for our division at? So we're going to put it at. Where we're going to put the answer for our division at? Which one can handle fractions? Yeah, the F8. Yeah, floating. Yeah, 8. And that's explained in your instructions, by the way. So we're going to be adding integers. We can add integers. We can subtract integers, and we don't end up with fractions. But when we get down to that division, you could have numbers that end up with a fraction, right? You understand? So when you look at your explanation about that lab, it's going to say store your answer for your division in one of your F8 data files. All right, guys. So I got no questions. We're through. You got a question? So what's new Wednesday? Still it's a grade, all right? You know, you turn it into financial aid.